welcome to the second semester of this course. In the second semester, we will talk more about trees, about some segment trees, binary search trees, some different tree requests like heavy light decomposition, link cut trees, centroid decomposition, and maybe something else in the end of the semester. We'll pick some interesting topics for the end of the semester just to keep things interesting. Let's go. So we will start this semester with segment trees. I have a whole lesson in the code forces edu section, so if you know about code forces, you may already seen this lecture soon. Today I basically repeat everything which I already taught in this lesson, maybe something else in the end, but basically it will be the same as on code forces. Let's go. So first of all, what is segment tree? If you Google segment tree, you will most commonly find another data structure. So it's kind of strange in terminology because there is another data structure which is also called segment tree, but it's completely different. So it's used for the computational geometry algorithms. It's basically you have some segments and you want to find segments which cover your point, something like that. So it's different data structure, and it kind of it was developed before this also, so it's kind of this name is reserved for this data structure. But I will use this name for data structure I'll discuss today just because of two reasons. First of all, this term is widely used in competitive programming. So some of you again are from code forces, so you may be familiar with this data structure. But in some theoretical books, like computer science books, they usually even don't mention this data structure. They go straight to binary search trees and stuff like that. And I think it's not good, because segment tree is it's kind of basic structure. So in order to be able to construct more complicated data structure, it's very useful to understand how the segment tree works, because segment tree give you some explanation about what operations you can do in logarithm time. Stuff like that. That's all in introduction. Now let's go to real stuff. So what is segment tree? You want to solve the following problem. You have some array of some elements. Of elements from 0 to 1. And you want to be able to perform two types of operation. First type of operation is to change some value in this array. So you want to be able to pick some element and change the value. IV, you basically made IV. Quite simple operation. And the second operation is to calculate something on a segment. Let's start with calculating the sum on a segment. So let's have the function sum from L to R. And this function will return the sum of all elements on this segment. So it will return the sum of elements from L, let's say, to R minus 1. I want to have this left border inclusive and right border exclusive. And I will try to always make left border inclusive and right border exclusive. So I need to have sum of all elements from L to R minus 1. Like this. Why are you so quiet? Is my chat working? Yeah, no, it's working. You are just quiet. Okay. Cool. Let's move next. Let's stop here a little bit. So, first, just for an exercise, if you don't have this first operation, if you only have this sum operation, so you have some fixed array, you will never change the elements of this array. All you want to do is to make this operation. You want to be able to calculate the sum on a segment. How can you do it using very basic data structures without any trees and stuff like that? Is it clear now? So if you don't have this set operation, you have only sum operation. How can you solve this problem using very basic data structures? With array, yes, array. What array? Well, if you just use a simple array, then you have this operation in constant time, this operation in linear time. That's what we want. You want to make this operation faster than in linear time. Yeah, prefix sum is a good solution. So if you don't need to change the elements of the array, you only need to calculate the sum on some segments of this array. You can pre-calculate the sums of all prefixes of this array. So you have this array, and you pre-calculate the sum on these prefixes and put these sums in some another array. And then you need to calculate the sum on this segment. You get this prefix minus this prefix will be equal to sum on this segment. Yeah, and you can do this trick with almost any operation which have some inverse value. So for sum you have inverse value. So if you have plus 6, you have minus 6. So if your operation have some inverse value, then you can perform this trick. Okay. Next. That's again. This only works if you don't have this set operation. So if the array is never changed, you have some fixed array, and you only calculate these queries. Yes, if you have set operation, you cannot do this trick because this set operation will change all these prefix sums. Yeah. Yeah. Right. Good. So how to make these two operations in faster than in linear time? Let's go. So what is the segment tree? Let's build the following binary tree. Let's have some array. Let's say we have some 5, 1, 3, 2, 6, 2, 4, 7. So let's have this array. Let's build the following tree. Let's build a full binary tree such that these elements are the leaves of the tree. So these are the elements of the array A. So this is array A. So we build the tree. These elements will be the leaves of this array, and each next element will contain the sum of all of the children of this element. Here we have some parent element, and here the sum will be 5 plus 7 will be 6. Here we'll have sum of these two elements, so 5. Here we have 8, have 11. And on the next level, again, we will have sum of these two. And here we have So this is the segment tree for sum operation for this array A. So we have this array A. So we can build this. This will be the segment tree for sum. So you have operation sum. We have this tree. Okay. Well, first, let's do it in a slow way. Let's go. So we have this array A. We build this tree. We can build this tree in linear time, right? So we just build this tree layer by layer. We put in first layer, then build second layer, third layer, and so on. The total number of all elements in this tree will be 2n minus 1. Why it is 2n minus 1? No, because here we have n nodes. Here we have n over 2 nodes, 3 nodes, and so on. The total number of all elements will be 2, but will be 2n minus 1. In this example, this tree is very symmetrical and beautiful just because this n is the power of 2. So if this n is a power of 2, 2 in power of k, you will get something symmetrical like this. If your n is not power of 2, you may build something not that symmetrical. So if you have like 3 elements, you may build something like this. Not very cool, but still works. I will not talk about trees like this just because I'm too lazy for this. So I will assume that I always have n equal to power of 2. So this tree is always the perfectly balanced binary tree. So I have all the subtrees are the same. So each element have exactly 2 children, like left child and right child and so on. So I always have tree like this. I'll never have something like that. Just for simplicity, you can actually you can take all the algorithms we'll discuss today and just modify them a little bit to work on trees like that. But it's up to you. Okay, why can I assume that n is equal to power of 2? Because if n is not equal to power of 2, I can always extend the array to the closest power of 2. So if you have n elements, you have this array A, you have n elements. You can add some more empty elements such that the total length will be power of 2. And this number of these additional elements will be no more than n. So this new n will be less than 2n. So if you extend your array to the closest power of 2, the total number of elements will be increased at most twice. So it will not affect the asymptotics. We will talk only about asymptotics today, mostly. Not exactly, but mostly we'll talk about asymptotics. So if you extend your array twice, that will not affect the asymptotics of the algorithms. So it's not good. Have this kind of thing in home task? Maybe. That's mostly technical stuff. It's not that interesting. So you can modify algorithms to work on these not perfectly balanced trees. It's just technical stuff. It's not that interesting, but you can. So let's go. Now. So we have this perfectly balanced binary tree. What is the total number of elements, or not total number of layers in this tree? The number of layers in this tree will be log n, like this. And we will build both these algorithms in such a way that the asymptotics of both this operation will be log n. So both this operation will depend on the total height of this tree, and the height of this tree is log n. So that both these operations will have asymptotics log n. Okay, that's all preparations. I'm just trying to save some time. If you have any questions. Okay, let's go. Now let's talk about algorithm. Let's see. We have this tree. Each element of this tree is responsible for some segment of the array. If you take, for example, if you take this 8 is the sum of these 2 elements of the array. So you have this 6 plus 2. If you take, for example, this 11 is sum of these 4 elements of the array. So it is 5 plus 1 plus 3 plus 2. and so on. Each element, each node of this segment tree represents the sum on some segment of this array. Well, like this 11 is the sum of these two elements, this 19 is sum of these four elements, this is sum of this element, this is sum of these elements, and so on. So each number here is sum on some segment of the array. The numbers in the leaf nodes are just the single elements, but we can represent single element as the sum on the segment of length 1. So let's say that these numbers are the sums of one element. So each element in this bottom layer will be just sum of one element. So one element is the sum of itself. Like okay, and this root element is the sum of all elements in the array. So again, it is sum of on the segment which contains all elements of it. It will be the sum of all these elements, and so on. Now, how to perform operations? Let's start with first operation. First operation, we need to change one element of the array and recalculate these sums. So if we change one element of this array, let's say you have operation set applied to this element and change it, let's say, to 5. So you take one element of the array and change its value. Now you need to recalculate the sums. You need to recalculate the sums which contain this element. Which sums contain this element? No, you need to take all the nodes which represents the segment which contains this element. You have exactly one node on each layer. Yeah. So you go from this element up to the root and recalculate all the sums. So you go here. Here you have 6 plus 5, it's 11. Now you move here, calculate this sum, it will be 22. And then you go here, recalculate this sum will be 33. That's all. That's how you recalculate all the sums after you change one element of the array. So you change one element here, and then go up to the root and recalculate the sums. So you could recalculate this sum, recalculate this sum, recalculate this sum. That's all. The total number of sums you need to recalculate is up to the number of the layers of the tree. And if you have the perfectly balanced tree, you have logarithm and layers. So the total number of elements you need to recalculate is log n. So this separation will work in log n. That's all. That's how you perform set operation. Very easy. You just change one element, recalculate the sums. Recalculate log n sums, you have the new modified segment tree. No, that's not very interesting because when we have simple array, we can modify in constant time. So it's much more interesting when you need to calculate this sum. Now let's see how this segment tree will help us to calculate this sum. Just erase this. Now, how will we calculate the sum on the given segment? Well, let's see. So you're given some segment. Let's use some more colors. Let's use this blue. Let's use this blue. So you're given some segment. Now let's have some. Oh. Is it visible? Strange, it's completely new mark. Okay. It's just new from the new box. No idea. Let's use another one. Okay, so you have some segment from L 2R. Again, L is inclusive, R is exclusive. Okay? So you need to calculate the sum on this segment. How this segment tree will help us to calculate this sum? Very easily. We will try to calculate this sum using the sums already stored in this segment tree. So we will build this sum from these numbers in this segment tree. For example, this sum, how can we construct? We can take this sum. Not exactly visible, but good enough. Plus this sum and plus this sum. So sum here will be equal to 5, sum here will be equal to 11, and so 4. So the total sum on this segment will be 5 plus 11 plus 4. Oh, arithmetics. My arch enemy. 20, right? So that's the plan. That's the plan. Again, what is the plan? We have this segment tree. And we need to calculate sum on some segment. We will take some of these pre-calculated sums and combine our segment from these pre-calculated segments. That's all. To teach lazy progression, we will do it next week. They will use some basic techniques about segment trees. Lazy propagation we will discuss in next lecture. Go. So, how can we find these segments? And well, two questions. First question is how to find these segments, and the second question is how to make it fast, because we need to kind of find the segments in log n time to make good asymptotics. Very easily. It's a very easy algorithm. So how we make this sum operation? Let's start from the root and make a traversal of the whole tree. So we just make a recursive procedure. We call it from the root, and each time we state it in some node x. If we're not in the leaf node, we just recursively go to the left tree and then recursively go to the right tree. So we recursively go here, traverse this subtree, then go right, traverse this subtree. If we do it like this, we will eventually go through the whole tree, so we will find all the segments we need. That's the operation. But if we just traverse recursively across the whole tree, it will take a linear time, yeah, because the total number of nodes in this tree is linear, yeah. So if we just make a recursive traversal across the whole tree, we will have a linear total time complexity. That's not what we want. So we will make two simple optimizations for this recursive traversal. First optimization is the following. Let's say we stand in some node x. So again, we have some recursive procedure, right? So in our recursion, we have some current node x. So we need to calculate the sum of all elements in this subtree. This subtree x represents some segment of this array. So this x represents some segments from here to here. Optimization number one. If this segment is not intersecting with this segment from L to R, so we have this segment from L to R. So if our recursion moves to this subtree, and we need to calculate sum of this segment, then in this subtree we don't have any important elements. So we can, when we move into this recursion, we can immediately return back, because in this subtree nothing is interesting. All elements, we don't need them to calculate the sum. So this is the first optimization. If we have something like this, we just return. I will write the code later. This is just some pictures. I will write the pseudocode. It's very simple. Second optimization. If the segment is completely inside, so if we have this node X, this node X represents some segment. And this segment is completely inside the segment from L to R. So we have something like that. Then we just add this segment to the result. So we add this segment to the resulting sum, because this segment is just a part of this decomposition. Yeah. So this segment of X is part of this decomposition of the given segment. So we, yeah. So we just add this, on segment and return. This is plus equal. I will write the code later. It's just some illustrations. That's all. That's all we need. So again, we make these two optimizations. So we make a full recursive traverse of the whole tree. Yeah. So we make a recursive procedure. We start from the root. Each time we try to go to the left tree, then try to go to the right tree. And we have only two optimizations. First optimization. If the current segment is not intersecting the given segment, we just return and do nothing. If it's completely inside, then we add this sum to the result. So we add this sum of the segment to the resulting sum, like this. So we go here, and again return from it. Let's illustrate it on this example. So we start from the root, then we go here, then they go here. This segment is completely outside. So we just stop the recursion here, go back, go to the right subtree, see this segment is completely inside, so we add this value to the result, and again stop the recursion here. Go back, go here, go here, go to the left, add this segment, go back from the recursion, go here, go to the left child, add this segment, go back, go back. So that's all. Good. Now, is it clear enough? I'm just trying to give you some time to ask the questions. So if you have any questions, just ask them immediately, because we have some delay between me and you. Okay, good. Now, let's calculate the total number of nodes we visit during this traversal. I claim that the total number of nodes we visit is about log n. Why is it true? Let's see, because almost all the time we have one of these two cases. Because in almost any recursive call, we have one of these two cases. Let's see why. Let's see. So if we don't have, if our current segment is not completely inside and it's not completely outside, so we have our current segment, yeah, and some elements on this segment are inside segment from L to R. So let's see, some segment is inside, and some segment, some elements are inside, some elements are outside. It means that we have one of the borders of this segment inside the segment of given X. Somewhere here, something like that. So one of the borders of this segment is inside this green segment. L or R is inside 7. So if we don't have this case and don't have this case, it means that some of elements are inside, some of elements are outside. Yeah. It means that one of the borders of this segment, either L or R, are inside this green segment. How many segments can have one of L and or R inside this segment? Well, let's see. On each layer of this tree, all these segments do not intersect. So these segments on each layer just split the whole range of elements into some non-intersecting segments. So on each layer, we may have at most one segment which contains R, and at most one segment which contains L. And we have log n layers. So we may have up to two log n segments with situation like this. So there are no more than 2 log n segments with situation like this. So basically, again, let's draw another picture. So we have this L, this R. So on each layer, on the first layer, we have like this segment and this segment. On the next layer, we have like this segment and this segment, and so on. So on each layer, we have only one segment which contains left border, only one segment contains right border. So there are at most 2 log n segment which contains one of the borders of this segment. And if we don't contain the border of the segment, then we are either completely inside or completely outside. So one of these optimizations will work. Now, what is the total number of invocations of this recursive procedure? So we start from the root. So we start from the root of the tree. Then each time if we don't have any of these cases, then we make 2 recursive calls. For root, for example, we make 2 recursive calls. Now here again, we check these 2 conditions. If we don't have this and don't have this, we make 2 recursive calls. And so on. For example, here we have one of these conditions, so we stop the recursion, then they go here, we stop the recursion, and so on. Here we have 2 recursive calls, again, here we stop the recursion, and so on. Yeah, it's exactly like here. Interesting. Now, in each of these nodes, we didn't stop the recursion. So it means we have this case. So these nodes are one of these 2 log n nodes. 2 log n nodes. So we have at most 2 log n nodes like this. So, and what is the total number of nodes? So we have these nodes plus these leaf nodes when this recursion terminates. So if we have 2 log n nodes here, then we have up to 2 log n nodes here. Because total number of elements in the tree, if you have full binary tree, then total number of leaves can be more than total number of internal nodes. Yeah, because each internal nodes give you like 2 branches. So if you have log n branches, then in the end you may have up to log n leaves, right? Yeah, clear now. Again, you're too quiet, so I will just repeat. That's my problem. I know. I just repeat the same thing until you until you confirm that you understand. So let's go. So the total number of nodes. So if you have log n these nodes, then we have at most 2 log n plus 1 maybe nodes here. So the total number of nodes we visit in this procedure will be up to 4 log n. Yeah. So the total number will be about 4 log n. That's all. Again, this is the total number of nodes we visit during this recursive procedure. And we don't do anything except this recursion. So that's the whole time complexity. Time complexity will depend on the number of nodes we visit. We visit log n nodes, so total time complexity will be log n. Whew. That's all. Still don't get why 2 log n again. Why we have 2 log n here? Because let's see. We make recursive procedure. In each recursion, we check if the current segment, so we just traverse this tree. If the current segment is completely outside, then we go back from the recursion. Just we don't do anything. If we are completely inside, we can go back from the recursion. So if we don't have this case and don't have this case, it means we are not completely inside and not completely outside. It means we are somewhere on the border of this segment. So we have this segment from L to R, and our current segment is on the border of this segment. So it's either it may be here, or it may be here, or it may be like this. So okay, the trick is that this green segment should contain one of the borders of this purple segment. So it should contain L or R. So one of these borders should be inside this green segment. And on each layer, these green segments do not intersect. So on each layer, we have at most one segment which contains L, and at most one segment which contains R. So the total number of these segments is at most 2 on each layer of this tree. And we have log n layers, so the total number of these segments should be up to 2 log n. This 4 log n, again, we have this recursion. This is the recursion tree, right? So we start recursion here, go here, and so on. We have 2 cases. We use one of these optimizations, or we have this case. If we have one of the optimizations, then we go to recursion and immediately go back. And if we don't have one of these cases, then we make 2 recursive calls, like here. Here we have just make 2 recursive calls. That's all. So let's calculate the total number of leaves in this tree. So we have these elements. In each element, we have 2 branches, and we have up to 2 log n such branching nodes. Each of these nodes have 1 input edge and 2 output edges. So it kind of increase the number of branches by 1. Yeah. So you have 1 branch, and here you have 2 branches. So each of these internal nodes just increasing the number of branches by 1. Yeah? So on the bottom layer, you have these leaves. Each leaf just terminates one of the branches. Yeah? So if you have 2 log n internal nodes, then in the end you will have 2 log n branches. And each of these leaves just terminates one of these branches. Makes sense? So the total number of leaves will be something like that. There are another ways of thinking about this, but that's actually the easiest way to think about this. So there are very small number of nodes which have branches. So most of the nodes just terminates. So in most of the nodes, you just go in the recursion and then immediately go back. So almost all nodes immediately terminates your recursion. There are only small number of nodes, about 2 log n nodes, in which you have some recursive calls actually. So total number of these nodes will be. Okay. Okay, you may want to rewatch it later. It's not that complicated. Just give yourself some time to think about it. It's not that important for the next part, so I'll just skip it. That's all. Now let's implement some code. So, how to implement this segment tree? There are different ways to implement segment trees. One of the classical way is just to have these nodes, and each node, so you have like something like that, and you have like 2 pointers to the left node, to the right node, stuff like that. You have like make it in C++ way, like left. Something like that. I never implemented like this, but it's actually possible. So you have some pointer to the left node, some pointer to the right node, and you have this sum int value. Oh, looks very industrial and okay, so it's possible to implement segment trees like this, and in some cases that's the most useful way to implement the segment trees, but not the fastest way. So you for each node you need to have this class, and in Java, for example, if you have a lot of small classes, then garbage collector will go crazy. So if you have like million of small classes, the garbage collector will say, okay, I can handle it, but it will take some time. So a lot of small classes is never good in Java, but and also it uses a lot of memory. So you have these 2 pointers. Each pointer costs you some memory and stuff. So and so on. So it's possible, but it's not that efficient. I will try to make another implementation. Which is kind of more efficient and it's not that universal. So for some problems you cannot adopt this implementation, but usually it can be used like this, and it's much more efficient. Let's see. So how we will implement this segment tree? We will implement it in the same way we implement the binary heap. So if you remember the binary heaps, we implemented this tree using a very simple technique. We just enumerate all the nodes in such a way that it's easy to see which element is the sum of each element, and so on. So we will just enumerate all the nodes from top to bottom. So we'll say, I need another color. This. So we'll say this node have index 0, this have index 1, 2, 3, 4, 5, and so on. So we'll just assign the indices for all nodes in such a way that it is easy to get the index of the child node when we know the index of the parent node. Again, it is absolutely the same as we did in the binary heaps. So if we have node X, then how can we find the index of its children? Well, it's quite easy. So the left child will have index to x plus 1, and the right child have index to x plus 2. Now, if we use 0 indexation, like if you start index from 0, then left child will have 2x plus 1, and right child will be 2x plus 2. That's all. And now we don't need these 2 pointers, because instead of these pointers, we just calculate the index of the children. Optimization. Second optimization. Second optimization is following. Let's see. When we apply these 2 optimizations, we kind of need to know the segment corresponding to current node. So when we make this recursion, we go to some node X. We need to know the borders of this current segment, of the segment which corresponds to this node, right? So we need kind of to store these borders of this segment, but I will not store this borders. Instead of storing these borders, I will just calculate these borders on the go. So when I use the recursion, when I am in the node X, I will know its current segment. So I will know the segment which corresponds to node X. It will be some segment from LX to RX. So I will not store this value in some fields of this node and something like that. I will just calculate these borders on the go. So when I'm in this node X, I have these borders from LX to RX. When I move from this element to its child, I will recalculate the current borders. So when I move from here to here, I will know that for this left segment, the borders are like from LX to some middle of this element, to some LX plus RX, something like that. And so when I move from here to here, I will just recalculate the current borders, and so on. So I don't need to store these borders in some additional memory. Oh, okay. Okay, now let's implement something. Okay, let's go. So first, let's implement this set operation. So we have this set operation. Set operation again just puts element v in position I. I will make it again. I will make both operation in recursive way. So I will make recursive procedure which make the operation in the given subtree. So I will take this operation and add 3 more parameters: the current node and its borders. And this will be recursive procedure which sets the element I to value v. Go. Let's see. So how to set the value of the element? If we are in the leaf node, how to check if the current node is the leaf node? The easiest way is to check that the length of the segment is 1. So if the length of this segment is 1, then we are in the leaf node. So if we are in the leaf node, we just set this value to this element and return from the recursion. I need some array to store these numbers. Let's say 3. So I will put this value in 2, 3. So I need to set value of node X to V, right? Yeah. So that's if we are in the leaf node. We just put this value here and return. If we are not in leaf node, then we need to go to the subtree which contains element I. Let's see. We're now standing here. We need to select one of these children which contains element I. How to do it? Well, let's put this to some variable m. Let's say m is the middle of the segment. Now, left segment contains all elements from Lx to m minus 1, and second contains from L to Rx minus 1. Yeah? So we need to change element I, so we'll check which of these segments contains element I and go to this subtree. If this I is less than M, then we need to go to the left subtree. We go to the left subtree. It means we call the same recursive function IV. For the left subtree, the node number is 2x plus 1, and the borders are Lx and M. And else we do the same for the right subtree. So we make the same recursive call for the right subtree. IV 2x plus 2 and R. That's all. So we just select one of the children and go recursively here and make this change inside this tree. Now, when we go back from the recursion, we need to recalculate the current value in the node X. So again, we are standing here, we make recursive call in one of the subtrees, make all the changes here. So we change this, and then we go back from the recursion. We need to calculate this value. So let's just recalculate this value. Just simply taking the sum of these. That's all. That's all. That's how you set the element of the array or of the segment. Clear enough? Let's have the second operation. Second operation. Where is this? Let's see. Again, second operation is to calculate the sum. So we need to calculate the sum on elements from L to R in the subtree X with borders Lx and Rx. And usually it's implemented the following way. Just by how it's called? There is a good word about this, but I don't remember. So we will assume that when we call this sum, it will return the calculated sum. Yeah? But it can calculate the whole sum on the segment from L to R. So it will calculate the sum of all elements from L to R which are inside the current segment. So you have, let me show. So we call this recursive function from some node X. This node X represents some segment. Yeah? And we ask him to calculate the sum on some segment from L to R. Yeah? So this recursive function will return the sum of all elements inside this subtree and inside this segment. So it will return the sum of all of these elements. Yeah. That's the easiest way to implement this section. So we'll just call this sum, and when it returns, it will return the sum of these elements. So it returns the sum of all good elements in the given subtree. Yeah. Good. Let's go. So first, let's see. Let's implement two optimizations. First optimization, if we are completely outside. So if these two segments do not intersect, so we have this segment from L to R and this segment from Lx to Rx. So they do not intersect if this L is greater or equal than Rx, or if Lx is greater or equal than R. Then they do not intersect. If they do not intersect, then this intersection is empty. We need to calculate, we need to find the sum of empty set. Sum of empty set is obviously 0, so we just return 0. If we're completely inside, so if this segment is inside this segment, means Lx is greater or equal than L, and Rx is less or equal than R. It means that we are inside, so we just return the sum of all elements in the subtree. So we just return this tree of X. If none of this, then we make 2 recursive calls. Let's calculate. First sum will be sum in the left subtree. So we calculate sum RR to X plus 1 Lx M. What is M? M, we need to calculate M. Again, we make recursive calls for this left subtree and calculate the sum of all elements here. Again, like, let me show it again. So we make recursive call for the left subtree, recursive call for the right subtree, and we need to calculate sum on this segment. The left call will return this sum, the right call will return this sum. Now we take sum of this plus this, we get the whole sum. So this is left sum of these elements. Now we calculate this sum. It will be the same recursive call for the right subtree. Like this. That's all. Now just calculate the sum of these elements. Yeah. So that is the whole code of the segment tree for the sum. Yeah. Nothing complicated actually. You can just use this code in C++ and it will work. Very simple. Now, what other operations can you do using segment trees? If it's only for calculating sum, it will be not very interesting actually. But the cool part is that instead of calculating this sum, you can calculate many other functions on the segment. For example, let's calculate the minimum on the segment. For example, if you want to calculate minimum on a segment, so we want function minimum from L to R, which return the minimum of all elements from L to R minus 1, like this. Okay. Is he Russian? Who he? Me? I'm Russian. Of course you hear it now. No, my Russian accent is pretty annoying. I know this. Oh. What I was talking about? Yeah. You want to calculate minimum on a segment instead of sum on a segment. We will try to do everything the same, but instead of calculating sum, we will calculate the minimum. So again, you have some segment tree. Let's have some elements like again 3, 5, 1, 6, 8, 2, 4, 5. So again, you have some array. We will build the same binary tree, but instead of sums, we will have minimums. So here we have minimum of on 3 and 5 will be 3. Here we have 1. Here we have 2. And here we have 4. And on the next level again we have this 1. Here we have 2. Here we have 1. So we do basically the same, but each time instead of sum we calculate the minimums. And again, both operations will do the same. When we need to change element, we change the element in the bottom row. Then we walk up to the root and recalculate these minimums. And when we need to calculate minimum on some segment, so given some segment, you need to calculate minimum on this segment. You split this segment into some elements, this plus this. Here minimum is 6, here minimum is 2. Calculate minimum of this, get the minimum on the whole segment. Yeah. Yeah. Just instead of, let's find all the places we need to change when we change from sum to minimum. Let's see. In this set, we need to change in the same thing here. So here we need to change this sum to minimum. So instead of this, we take the minimum of 3 2x plus 1 and 3 2x plus 2. In this function, we need to change here. So here we have plus. So again, here we need to make minimum of S1 and S2. And there is one more place we need to change. Yeah. I missed this comment. Sorry. One more place we need to change is this 0. This 0 represents the sum of empty set. Yeah. So we have empty set. The sum of empty set is I don't say it's obviously 0, but it's how to say. It's very useful to keep the sum of empty set equal to 0 because it will keep all other arithmetic good. So here, when we have minimum, you need to find minimum for empty set. Minimum of empty set is something more complicated. So if you, philosophically speaking, if you have no elements, it's kind of hard to pick the minimum elements if you have empty set. But it's very useful to just say that the minimum of empty set equal to plus infinity. Again, it will keep all the calculations correct. It's kind of strange in philosophical way, but it's I mean it's working. It's working. That's the main thing. So if we just place plus infinity, then it will work. Why it is plus infinity? So what element we need to pick here? So here we need to pick something called neutral element. So we need to put here some element which will not change the value when we apply this function. So if we have this plus infinity and then we add one more element, we will have minimum of this element and plus infinity, and it will give you this element. So it is something which will change to the first element when we add this first element. So when you add first element to the set, you apply this function minimum, and the result is this Kelvin element. The same is with the 0. When you apply plus function to 0 and something, you get this something. That's all. We are a little bit of time. Okay. Will we have enough time to talk about persistent trees? I think we need some more time to talk about persistent trees. Just to make it more interesting, right? Because this all is in the code forces lesson, so we need to add something. Let's go. Next, what other operations can we use in this in the segment tree? We can use basically all the operations which have the associativity property. So if you want to have some operation, so you have the operation sum from L to R. Let's change it to something. Let's give it another name. Let's have some calculate. So you calculate something from L to R, and this something is just a result of some operation. Let's say we have L, then some operation L plus 1, then some operation and so on, then some operation R minus 1. To have no no, usually segment tree is the binary tree. Why don't you can make it ternary tree. You can make it ternary tree as the segment tree. Now each time here you will have not 2 elements but 3 elements. But why? 2 is enough. 1 is a little bit less. Yeah? If you have only 1 child, it's not a good tree. If you have 2 children, it's again the height of the tree will be log n. So 2 is enough. Let's go back again. So you want to make some operation which calculates something on a given segment. And if this operation have the associative property, so if this operation is associative, so it means that you can apply associative DVT. So it's very simple property. It kind of means that you can apply operations in any order. So if you have like A something, B something, C, then you can apply these two operations in any order. So you can apply operation to A and B and then apply C to the result. Or you can do it like this. You can apply B to B and C and then apply A to the result. So if you have some operation which have this property, then you can use this operation in your segment tree. Okay. Now let's see. Why do we need associativity? Where we use that our operation is associative? Let me just change the code, and you think why we need this operation to be associative. So we need to change it here. So we just change it here. We change it here. And here we use some neutral element. So these are 3 points of attention. Like all the rest code is the same always for all operations. Again, let's go back. Why we need this operation to be associative? Basically because of the way how we calculate the sum. So if you remember how we calculate the sum on a segment, what we did when we try to calculate the sum on a segment. So we have some segment. We try to split the segment in some subsegments, then calculate sum on each segment, and then combine them in the big sum. Basically, we changed the order of the operations. Yeah, so we have like A, B, C, D. So when we calculate sum on this segment, we may want to calculate it in this following order. We calculate this sum of A plus B. Yeah. So this sum is in this node of the segment tree. Then we calculate this sum in some another node of the segment tree. And then take sum of these two sums and kind of hope that we get the sum on the whole segment. Yeah. Plus. So when we use segment tree, we apply these operations in some strange order. So first we calculate this sum, then take some of these, and so on. So the order of operation will change when you try to calculate it using the segment tree. And to keep the result the same, we need this associative property. Makes sense? Okay. Now, what operations can you use when they are associative? Many operations are associative, like minimum, maximum, sum, product, many products like matrix products, modular products, and so on. Greatest common divisor, some bitwise operations like bitwise AND, bitwise OR, bitwise XOR. Right, a lot of, we will discuss some, sometimes whereas we have some more complicated operations. So for some problems, you may need to have some custom binary operations, and just to prove by yourself that your operations you construct are associative. Sometimes it happens. So sometimes in each node you have some free values, let's see, and you combine these triples using some strange rules. And you need to prove that your strange rules give you some associative operation. Sometimes it happens. Okay. Whew. Cool. Let's move to the final topic I want to discuss today. Let's have something interesting. Let's make a persistent segment tree. If you remember, at some point in the last semester, we was talking about linked lists, I think. So when we talked about linked lists, we built it. Yeah, I was about. I think it was about. Yeah. I think it was about the linked list. So when we talk about linked lists, we built a persistent linked list, and now we'll try to do the same with the segment trees. So what is persistent data structure? Let's remember what is. Okay. Now let's go back again. Let's go back. We already discussed it few lectures before in the first semester, but let's just do it again. So sometimes you want your data structure to remember all the previous states. So you have some initial state of your data structure, then you apply some operation. Yeah. So after you apply some operation, you have a next state of your data structure. Yeah. And sometimes you want to be able to access both the previous state and the new state. Well, like, let's see, you have, like, for the segment tree, yeah, you have your current state of your segment tree. So you have some array. Let's have some small array. Some array of 4 elements. 3, 1, 6, 5. Yeah. Why I always have the same numbers here? Yeah. I have really small imagination. Yeah. Okay. And so this is the current state of your data structure. And then you apply some operation which changes the current state. Yeah. So you apply some operation. So you make operation set. Let's check. For example, let's set this element. Let's send an element of index 2 with value 4. So now this array equals to 3, 1, 4. And with standard data structure, you just have this state. This is your current state. So if you apply next operation, you will apply this operation to this current state. In persistent data structure, you want to be able to apply operations to both these states. So you want to have this version 1 and this version. What just happened? No idea. So you have these two versions, and you want to be able to access them both. Yeah. I hate this marker, sorry. let's have another one. Version 1, this is the version 2. So you want to be able to access both these versions in the same time. So how you make it work using the persistent segment trees? Very easily. We used almost the same techniques with linked list, actually. Techniques called path cloning. Okay, let's go. So we have here, we have this segment tree. So we have this segment tree, 3, 1, 6, and 5. Well, let's have segment tree for the sum operator. Yeah, we have this 4, we have 11, we have 15. So we have this nice segment tree, yeah, for this state of the segment tree. Now, we want to apply this operation. So we want to change this element to 4. But we don't want to forget the previous value. So we want to remember that the new value of this node is 4, but the previous value was 6. So we'll do a very simple trick. We will just clone this node and make a new node with the new value. So we have this old value and another node here with the new value. I hate these markers. What's wrong with them? I don't know, this is new pack of markers. For some reason, some of them don't work. So this is the new version of this node. Now, we go up to the root and try to update our segment tree. So we go to this node and try to update value here. So the new value here must be 4 plus 5. 9. It's 9. But we don't want to forget this old value. So we clone this node and create a new node with value 9. And just put this node as the left child to here and this node as the right child to here. So here we have two versions. First version is this 11, and it has two children, 6 and 5. And second version is this 9, and it has two children, 4 and 5. So in this version we have 11, 6 and 5. In this version we have 9, 4 and 5. And now we do the same for the root. We have this root, and we try to update the value. So the new value here must be 13. So we change this 15 for 13, and when we change, we just clone this node to the new version, make the new version with the new value, and put this element as the left child and this element as the right child. That's all. That's all. Now, on this picture, there are two versions of the same tree in the same time. So, if you start from this root, you get the first version of this tree. If you start from this root, you have the second version of this tree. And you can access both these versions in the same time. Yeah? So, if you want to do something in the first version, you just start your recursive procedure from this root. Yeah? You just call the recursive procedure. I erased it, but that recursive procedure. You just call it from this root. And when you want to access the second version, you call the same procedure, but from this root. And you will have the result in the first version or the result in the second version. They don't conflict. You can hold here, you can hold here, and you'll have some results for the first version, for the second version. Yeah. The bad thing is each of these updates will add log n new nodes to your data structure. Yeah. So the number of nodes will be increasing when you want to maintain all the previous version. Yes, right. So each new version will give you log n new nodes. That's not perfect, but usually it's not a big problem. So, because you kind of want to maintain this log n information, you need to have some log n memory to maintain this log information. So it kind of makes sense, yeah. So, because you want to save this log n number somewhere, so you need to have some memory. So you don't waste memory here. So each node contains some important numbers, some on some segment which will you use later. So it looks like we don't waste memory anyway. But yes, each new version will give you additional log n nodes. That's all. You cannot do it using this technique we discussed when we implemented this. So you cannot just enumerate nodes in such a way that left child is 2x plus 1 and right child is 2x plus 2. So you really need to have some pointers from each node, from the current node to the children nodes. So you know, because these two elements have the same left child, yeah. So you kind of need to implement this whole thing. So each node must have two pointers, pointer to the left child, pointer to the right child, and so on. Okay. now what you can do again? What you can do? You can take one of the version and call any of the functions we discussed the first. So, for example, you can take the first version. And call some function. So we start from here, 0 to 2. So we just go to here to the left child, calculate sum. So go calculate this, then go to the right child, go here, calculate this. So this plus this, the sum will be 10. That's all. Also, you can modify every version. So this is the fully persistent data structure. If you remember what it is, it's called fully persistent data structure. You can modify any version of this data structure. So basically, what you can do, you take the first version and make another set operation and produce another version. So now you have this first version. You make this set operation, produce the second version. What you can do is to take first version again and make another set operation, produce the second. You can do it like this. Or you can take this second version and make another set operation, produce like fourth version. So you can take any version of data structure, apply any set operation, and produce another version of this. So you can branch from any place of this version tree. You can branch and make another version. Why you want to do this? It's a good question. We may discuss it next week. So there are various different problems you can when you can do something like that. We will discuss some of the problems later in this course, but for now it's not important. So for now, you may think about it like about some magic. So you have some data structure which is possible to access some previous versions. Why you want to access the previous versions? It depends. In some problems, it's important to have access to all previous versions, because the logic here kind of the following. So you make some operations, and then when you have request, it's hard to understand. It's hard to explain without some more explanation. Let's do it in few minutes. maybe next week, maybe in 2 weeks. Okay, so at some point we'll discuss some problems which actually uses this property of persistent data structures. Not today. Yeah, it's already too late. Okay, so thank you for joining me today. See you next week. I will publish some home tasks, and we will discuss the home tasks next Saturday, right? I think we'll keep the same schedule as the previous semester, so we'll have lectures on Fridays and home task discussions on Saturdays.